with today's session. Today's session, as I mentioned, is about introduction to theory of inventive problem solving, which is also called as TRIZ, or in fact, introduction to TRIZ, which is also called as theory of inventive problem solving. Hmm? So, see, in typical ideation methods, what is it that you observe? Typically, when you brainstorm, what happens? You come up with lots of ideas, and then you have to evaluate those ideas to identify the good ones. Have you experienced that? All of you must have, and we have all solved some problem or another at different points of time in our lives. So have you experienced that when you usually brainstorm, you come up with lots of ideas, of which just one or two may be good, and the remaining are not really worthy of further exploration? Has it happened with you?
Yes, sir.
So when that happens, you may not know at the outset that the bad ideas are bad ones. You may think that this is also a good idea, and you may end up evaluating it, and you finally realize, oh yeah, it doesn't work. Has it happened?
Yes, sir.
Yes.
So that's a waste of time. So this is the typical trial and error method where we brainstorm, we ideate, and we come up with lots of ideas, and just a few of them would work. Many may be promising, but just a few of them would work, and we end up wasting a lot of time. In entrepreneurship track, when you want to start your company, or when you are in your job, or when you are in a life critical situation, life threatening situation, do you want to go into a trial and error method, or do you want something which is more efficient?
Efficient.
Time crunch, then more efficient.
The more the time crunch, the more the importance of being, in the market on time, or being able to find a solution faster than others, faster than your competition. Remember the deer and tiger story that we started the course with. So whenever the time is of essence, whenever the survival is of essence, you do not want to go to the conventional trial and error method. And what you would ideally want is that, okay, I just want the golden nugget. I want the idea that simply works, and I want to simply implement it. Am I right? That is what all of us desire. And the good news is that this toolbox, TRIZ, that I'm introducing you to, can actually help us do exactly that. How does it do that? This is just a small introduction, and during the course, we will actually learn various TRIZ tools and try to do exactly this thing. Okay. So before we move ahead, let's watch a very short movie about what TRIZ is. Give me a second. So, what was happening here? Who can tell me? What did you capture out of this?
It
So,
showed the
okay.
evolution of ideas over the time by various scientists and how it eventually, like in modern era, it led to patents. Like people started doing patents of various ideas.
Mm-hmm.
Like in the very end, so it seems that a person like kind of synthesized or like synthesize all those ideas from the different patents, or like to synthesize the knowledge that he could gain from different kind of patents to some kind of a book type or a like set of rules kind of something come up with.
Interesting. So good. So this movie is actually, so this movie and a few more that we will see today were generated as a part of European project on popularizing Triz. So this is a kind of this is a multilingual movie. In fact, you would see that the titles were here in English, but there are other versions of the movie where titles are in French and Italian and others, so that the whole European Union could know more about Triz. And what we actually are talking about when we talk about Triz is it's a Russian acronym. So we are talking about theory of inventive problem solving, but we are always using the word Triz instead of tips. So the Russian phrase summarizes or gets acronymized to Triz, but in English we call it as theory of inventive problem solving. So there was this a person called Genrich Altshuler, who was an inventor by nature. Even as a child, he would think of trying to find solutions, inventive solutions to problems. And he studied more than 2,000 patents as a part of his exploration of ideas. So what he always felt was that just like there is the science of physics or chemical equations, or there is this mathematic levels of abstraction of algebra and so on, or trigonometry and so on, through which, without even getting to know the real numbers or the real problem, we could solve it on a paper. For example, in chemistry, I know that if I mix copper sulfate with say sodium, I will get some compound which is, I do not really need to do that experiment. Just by the nature of, or my understanding of the chemistry or the phenomena, how chemical reactions occur, I can always identify what will be the output. So Altshuler felt that the same should exist for problem solving. And he wanted to find patterns in various problem solving techniques. And he studied more than 2 lakh patents in a period of over 20 years. So, we've not, I'm not sure how many of you have read even 1 or 2 patents. A few of you may have, but most of us do not read patents. It's not easy to read them. This guy read more than 2 lakh patents. And today, accessing those patents is very easy. We have internet, we have USPTO website, we have Google Scholar, we have patent.google.com, and so on. So many places where all these patents are consolidated. We just need to do a search and we will get all the patents that we want to study. In those times, there was nothing like that. We had papers, patents. In fact, they were typed and typed भी नहीं कहेंगे. They were stylosized, and that kind of papers on which those patents were written. And this guy actually read so many of them, and he rated them. He rated those inventions on a scale of small improvements to discoveries. He classified them to identify trends and proposed a higher level abstraction of finding solutions to problems. This methodology of using a higher level of abstraction to find solutions to problems is theory of inventive problem solving, or in Russian, you would use the other expansion, and it's called Triz. Okay. So typically, if you look at this equation, 3x squared plus 5x plus 2 is equal to 0. The solutions to this equation are -1 and -2 by 3. but do you ever solve it by a hit and trial method? Okay, so sometimes you would, but let us say I gave you an equation like 9x squared plus 2x plus 5. Would you be able to simply factorize it and solve it by a hit and trial method?
So we may, but it will take time, but we have a systematic method in place, so we will use that.
Yes. So the systematic method in place that we have is, we say that, okay, this 3x squared plus 5x plus 2 is equivalent to ax squared plus bx plus c. I know the standard solution for ax squared plus bx plus c, and I will simply replace a, b, and c in this solution to arrive at my answers. Am I right?
Yes, sir.
So this is what we do in mathematics. Let us look at another example. Physics. Let us say I'm heating this particular rod. Let me just put my laser pointer there. Let me say that I'm heating this particular rod from this x from the left side. If I'm heating it from the left side, what happens? I want to find the temperature as the thing moves towards the right. If I have some kind of information about this material and the heating mechanism and so on, I would use the double derivative minus k d2t by dx square is equal to qx, the kind of energy I have invested in it. If I do not have that kind of information, I will use the del operators. If I do not have even that kind of information, I will use Laplace transforms. And these are all simple solution operators. We know that if it is the Laplace transform LT is equal to Q, then to find the value of T at any given point, I just need to do L inverse into Q. And I will be able to arrive at answers. So in the same manner, Altshuler proposed different levels of abstraction for Triz. The most fundamental, most basic level is called technical contradiction matrix. Above that is called physical contradiction matrix. And you will notice that as we go higher up in the level of abstraction, even in physics or elsewhere, we need some additional information. So we may need to do some additional homework. And the still more higher level of abstraction is substance field diagrams. We'll talk about technical contradictions and physical contradictions in this course. Substance field diagrams, I will introduce them to you. And depending on your project basis, we could actually go and use this particular abstraction in much more detail. Otherwise, in the class, we will just have a simple introduction of the substance field diagrams. But the intent of sharing these two examples with you was that the method that we use in regular sciences and mathematics of going to a higher level of abstraction is the same method we will use for inventive problem solving in the projects that we just talked about. Any questions?
So I mean, the different level of abstractions, like how would I was not able to really get like what, like if we are not able to solve via technical contradiction matrix, then we would be moving to physical contradiction.
Yes.
And so they would be dealing with different kind of parameters or like.
Yeah.
Okay.
So see, how to move from one level of abstraction to another, that is something that we will learn as a part of this course. Don't worry about that aspect. That is something we will anyways learn. But what is important is to realize that that is what we anyways do in other domains of our work also. That is what we anyways do in other domains of our work also. So it's nothing new. We as engineers are actually used to it. Are you able to see that?
So it's like applying those scientific principles only, but to this new kind of creativity or inventing problems, finding innovative solutions.
It is applying the same principles to problem solving as we know it.
Okay, sir. Okay.
So we today know problem solving only through hit and trial method. Now we want to say, okay, we know science. we know mathematics, and we know that we can apply better, more advanced methods for problem solving in these domains. And that is what we will use here also. Okay. So